So let's get started. Hello, everyone. It is my pleasure to welcome you today to the doctoral dissertation defense of Benard Tabu. Benard got his bachelor's in education physical from Lowell University in Uganda in 2010, and his master's in science and physics from Makerere University in Uganda in 2017. He joined Lowell and our research laboratory, the Engineering Energy Laboratory, in 2019. Have been doing cutting-edge research on how to get hydrogen from solids using plasma. It has been an excellent scholar and a team member. It has certainly been a great pleasure to be working with him through all these years. So for this morning, Benard will be presenting for 45 minutes. 45 minutes. Okay. Between 40 and 45 minutes, right? And after that, we will open the floor to questions from the general audience. After some round of questions, right? We will have to excuse the audience, and the committee will just have questions directly with Benard. Nothing else, so please, Benard.
Yeah, thank you so much, Professor Trellas, for that exceedingly kind introduction. And thank you so much, everyone, wherever you are, for taking your time to attend my doctoral defense entitled Hydrogen Production from Polymeric Organic Solids via Atmospheric Pressure Non-Thermoplasma. So this is the quick snapshot of what we are going to look at. We shall start with introduction, which includes motivation and background, as well as goals and the objectives of the research, and then followed by plasma reactors for hydrogen production from low-density polyethylene. And then we shall look at hydrogen from cellulose and low-density polyethylene, where we shall pay attention to spectroscopic analysis and electrical model, as well as solids characterization. And we shall conclude and have some recommendations. So the motivation of this study is actually the green hydrogen for energy storage. Now, the global energy consumption is expected to increase by 50% by 2050. That's according to the US Energy Information Agency. And currently, as you look on this graph, we see that most of the energy is actually derived from fossil fuel. And this vast and this overdependent on fossil fuel actually releases vast amount of carbon dioxide. And one study done by this group called Lowell estimated that if the business is remain as usual, then we shall have up to 55% increase in carbon dioxide emissions by 2050. So that means we really have to scale up the utilization of renewable energy. But one problem with the renewable energy is that it is intermittent. So for continuous operation, you actually need batteries. And most times these batteries are really very expensive. And that's why hydrogen becomes a viable alternative. It's a clean fuel and has highest energy density, 120 megajoules per kilogram. And it's one of the most abundant elements in the universe. But the problem is that there's actually no natural sources. So we find it embedded in complex compounds like natural gas, water, and solids. And we also realize that solids such as organic polymeric waste has a significant source of this hydrogen. So let's look briefly at the source of organic polymeric waste. So it's really enormous. According to World Bank, currently over 2 billion metric tons of this waste is generated annually, more food waste than green. But also when you look at when you look at plastics, paper, and cardboard, that also forms a very significant percentage. For plastic, it's mainly single-use plastic, which consists of low-density polyethylene and polyethylene terephthalate. And it is also expected to increase up to 26 billion metric ton by 2050, according to GEA. And currently, the recycle is still very low. Now, for biomass, it's mainly agricultural waste, paper, cardboard. The source is also enormous. It's 100 billion metric tons annually, according to CHO. And currently in the US, only 68% of the cardboard is actually recycled. So that means valorizing this plastic using renewable energy would have a very significant, potentially significant economic and environmental impact. So that's why we focus on two model feedstock. For plastic waste, we focus on low-density polyethylene, which consists of a long-chain hydrocarbon, and mainly it is used in packaging bags and thin film coatings, squeeze bottles, pipes, and cables productions. And for biomass waste, we focus on cellulose, which consists of anhydrous glucose ring bonded by 2,4-glycosidic bond. And mainly we find it in wood, cotton, crop residues, and linen. So briefly, let's look at some of the technologies which are used for hydrogen production from solid. Conventionally, it has been via thermochemical, where heat energy is used to initiate and control the reaction. And it can be pyrolysis in the absence of oxygen, or gasification in the presence of controlled amount of oxygen. And this is a very energy-intensive process and also releases secondary waste. Now, plasma has also been used in waste treatment, and plasma is partially ionized gas consisting of electron ions and some heavy species. And plasma exists as there are two broad categories. One is thermoplasma. So in this case, the electrons and heavy species have the same uniform high temperature. And this kind of plasma is characterized by a high electron number density. And some examples include the arc, inductively coupled plasma, as well as microwave. But also we have a non-thermal plasma where the electronic energy is really very high compared to heavy species. And some of these examples include glide arc and trans arc. This is actually what we have in our lab and what we have been working on. And also we have glow. So the thermoplasma has been used extensively for waste treatment, with a number of plants piloted in Europe, America, as well as Asia. But if you need a process which requires a lot of selectivity, then it is limiting, and also it has low energy efficiency. So that's why we envision this research as an initial step towards production of hydrogen from organic polymeric waste via direct use of electricity. So let's look at the goal of the research, which is to study the use of atmospheric pressure non-thermal plasma to produce hydrogen from organic solid polymers, particularly plastic and biomass. And this has been achieved by three objectives. One was to design and characterize non-thermal plasma reactors to produce hydrogen from polyethylene and cellulose. And two, to assess the performance of the reactors in the production of hydrogen. And three, to evaluate the performance of the reactors to produce carbon co-products. So let's look at plasma reactors for hydrogen production from low-density polyethylene. So we designed two different reactors, and one of them is a trans-arc, which consists of its pin-to-plate configuration. And the plasma is formed at the tip of the electrode and impinges onto the feedstock. And then that results into production of hydrogen and some other gas species. And some of the operating parameters includes voltage level, electrode feedstock spacing, as well as flow rate. Now, in this configuration, the feedstock is actually electrically coupled. So with that, we have direct control over the power delivered onto the feedstock. Then another one also, the second one is actually gliding arc. We term it glide arc, which consists of 3 electrodes. And the arc is formed at the minimum electrode separation. And as the gas flow in, it is driven down, and the plasma is driven down and impinges onto the feedstock, and the interaction results into production of hydrogen and some other gas species. So some of the operating parameters include voltage level, the minimum interelectrode spacing, as well as the flow rate. So here the feedstock is electrically decoupled, so we can use it for treating stream of feedstock or even surface treatment. So we also carried out computational thermal fluid models to characterize our reactor design using SolidWorks flow simulation. And in this model, we assume that the plasma is a volumetric heat source of 100% porosity, and we wanted to see the temperature distribution within the reactor chamber. And what we see now is a temperature distribution for a representative condition of 1.75 watts for transfer arc and a flow rate of 0.1 SMPM and the spacing of 5 millimeters. We see that the temperature at the center over the feedstock is actually highest, but as you move away from the center radially, it actually reduces. But also what is so distinct is that near the wall of the reactor chamber, we see it is at an ambient condition. So that means we can really operate this reactor without extra cooling. And then for the glide hacked, we see that over the surface of the feedstock, we have three-fold symmetry, and that depicts actually uniform treatment of the feedstock. And the temperature is relatively much lower than the one of a transfer, mainly due to convective cooling and the higher flow rate. So we also look at the flow dynamics in the reactor. We see that for the transfer arc, the velocity is actually highest at the center, and as you move away from the center, it's less pronounced, and that probably depicts the formation of a crater-like depression, and that also helps us to know what kind of feedstock we should use. If you use powder, probably it would really get out or get scattered. And then for the gliding arc, we see that the velocity is not much pronounced over the feedstock, but also we see a lot of recirculation here, which is very pronounced, and that could probably lead to recombination of hydrogen. So we look at the surface temperature over the feedstock for a different span of thermal power per unit volume, which is the heat dissipated per unit volume. And for the transfer arc, for different flow rates of 2 SMPM and 4 SMPM. So for the transfer arc, we see that as the thermal power per unit volume increases, the surface temperature also increases, but it's very comparable for these flow rates. And the same observation is actually made when you look at the average surface heat flux, which is very, very comparable. So that means in this case, the flow rate has a very insignificant effect. And for the glide hacked, we see that yes, the thermal power per unit volume increases. The average surface temperature increases with the thermal power per unit volume, but it's highest for a lower flow rate of 2 SMPM. At a lower flow rate, you have less convective cooling. And for the surface heat flux, also it follows the same trend. So this is our experimental setup. We are 2 plasma reactors placed side by side for easy operations. And as the gas flows in here, so this the plasma is formed and hits the feedstock, and the interaction results into production of hydrogen and some other gas species. And here is where we sample the gas. So some of the diagnostics for imaging, we use optical and high speed, as well as showing visualization. And then for the electrical, we measured current, voltage, and power using oscilloscope. And also for gas composition, we use gas chromatography. And in this condition, we took low density polyethylene. We used nitrogen as a working gas, and the treatment time was fixed at 30 minutes. But for the gas sampling and the electrical measurement, we took at the interval of 5 minutes. And this is actually the shearing visualization setup. So what shearing does is that because of the density variation in the reactor medium, it resolves that, and you're able to see that as a turbulence, like cloud. So it consists of a light source, which is very small aperture and is incident onto this reactor chamber by this collimating lens and focus onto the camera. And this knife edge adjusts the sensitivity of the setup, and we are able to see the plasma at a much lower frame, and we wanted to know if the dynamics of the plasma correspond to the hydrogen produced. So this is the optical imaging. So what I'm going to show you here is the video for the trans arc under these operating conditions. So the plasma is formed at the tip of the electrodes and impinges onto the feedstock, and that results in the production of hydrogen and some other gas species. So what we did was we wanted to look at the plasma dynamics over a different range of voltage level as well as the flow rate. And we see that as we move horizontally, we see that as the voltage level increases, the plasma intensity also increases. But as you go down vertically, we also see that as the flow rate increases, the plasma intensity does not really increase significantly. So here we the flow rate does not have a very significant effect. So for the experiment, we took actually two experimental conditions. We took voltage level of 20 and 30, and to expand the matrix, we consider the spacing of 5 and 10 millimeters. And this is the optical imaging for the experimental condition which we took. So we took the video at the start of the experiment and at the end of the experiment. Now, for these different conditions. But we see that for a shorter spacing, the plasma is really very stable and has a very intense interaction. And it is even more pronounced at a higher voltage level of 30, because at higher voltage level, you have higher power deposited, and then that results to high production, enhanced interaction of plasma with the feedstock. Whereas at a longer spacing, the plasma is really very weak, and it also interact with the feedstock very, very weakly. So this is the optical imaging for the glide act under this condition of spacing of 5 millimeters and the voltage level of 75 and the flow rate of 2 SMPM. So when you look at this video, we see that the plasma is formed at the tip of the electrode. As the gas flow in, it drives the plasma, and this impinges onto the feedstock, and then that results to interaction of plasma with the feedstock and production of hydrogen and some other gas species. So we look at a wide range of spectrum, the voltage, different voltage level and flow rate. We still see that as the voltage level increases, the plasma intensity increases. But also, we also saw that we see that at some point of flow rate at a certain voltage level, the plasma is formed at the tip of at the minimum electrode separation, but it cannot be driven down. For example, at a lower flow rate of lower than 2 SMPM, the plasma is held up, it cannot be driven down. And at a higher flow rate, the plasma is driven down very fast and does not reach the feedstock. That's why we see these empty spaces. Now, for the experimental condition, this is the condition which we took. This is optical imaging for under different experimental conditions. Still, we took at the start of the experiment and at the end of the experiment. And we see that at the lower flow rate, there's enhanced interaction of plasma with feedstock, because two things: at lower flow rate, there's less convective cooling, and also secondly, there's higher residence time of the gas. So the plasma would have a sufficient time to interact with the feedstock. And this is actually the Schwerin imaging for the transact. It mimics what we saw initially under the optical imaging. So here we see that the plasma is faintly visible, but as it impinges onto the feedstock, there's a formation of this turbulence which is emanated near the surface of the feedstock. And we wanted to see if we can try to get a qualitative description of correlation of this with the hydrogen produced. And what we did was we took a dummy feedstock of glass quartz, and when we subject it under the experimental conditions, we see that yes, the turbulence is formed, the plasma is faintly visible, and the turbulence is formed, but it's not really very pronounced. So when you look at the one for the feedstock, then we see that the turbulence is actually more pronounced, and it's even higher for a higher voltage level and shorter spacing, and that's the condition where we had the highest yield of hydrogen. So we concluded that yes, the turbulence represents correlated to the production of hydrogen, the higher degree of turbulence. Now this is for the glide path. So we had to reduce on the frame rate, and for us to see this, the axe glides slowly along the electrodes, and as it impinges onto the feedstock, there is this glow, and we wanted to see also the correlation with this glow and the hydrogen production. And we took for a dummy feedstock, we see that as the axe impinges onto the dummy feedstock, then the glow extinguishes. Actually, the glow extinguishes. The plasma extinguishes without the glow, whereas for the feedstock, the glow is actually more pronounced, and we correlate this to higher hydrogen production. So I also want to show you the sample characterization. This is using the optical camera. The pristine sample is white, very smooth on the surface visibly, but when you subject it to plasma, then we see that for a shorter spacing, there's enhanced interaction, which is higher at a higher voltage level of 30. And because at higher voltage level, you have higher power delivered onto the surface. And also shorter spacing means the electron travel faster with less collision, and that results to enhance production. And for the glide path, we see that the interaction is more significant at lower flow rate of 2 SMPM compared to 4 SMPM. And at lower flow rate, we have less convective cooling, as well as higher resident times of the gas, which enhance the interaction. So we were also interested in the electrical characterization because we want to know the efficiency of the system. And we measured the current and the current voltage, and this is the power as a function of the treatment time for the different conditions. We see that as the treatment times increases, the power remains relatively the same. But what is distinct here is that at higher voltage level, irrespective of the spacing for the transfer arc, the power is really high, much higher than at the lower voltage level. And for the glide path, we also see that irrespective of the flow rate, at the higher voltage level, blue and purple, the power is actually much higher. And also when you see for the glide path and transfer, glide path actually had a higher power compared to transfer because we are using 2 plasma power supply in that case. So we assess the performance of this reactor for the production of hydrogen in using 2 different parameters. In this case, we looked at hydrogen production rate and hydrogen production efficiency. And this is the hydrogen production rate for a transact. We see that for a higher voltage level of 30 and shorter spacing, the production really significantly higher, and it increases rapidly within the first 15 minutes and tries to level off. And here we have a low production rate, probably because at that's the time the feedstock is getting melted. Like more energy is spent in melting the feedstock. And for the hydrogen production efficiency, it follows the same trend. It's highest for the higher voltage level and lower spacing. And this is for the glide path. So for the glide path, we see that at a lower lower flow rate of 2 SMPM and higher voltage level, the production is really much higher. Still, it increases within the first 15 minutes and tries to level off. And when we look at the higher hydrogen production efficiency, it actually follows the same trend. But overall, in these results, we see that the hydrogen production in both cases, both the transact and glide path, are actually comparable. So with this, we move to the next and then the second last aspect. So this is the second phase of our research basing on our previous results. So here is the interaction between plasma and the 2 feedstock. So we see that this is actually the schematic. So we see that the highly energetic electrons, as it vibrates, then it breaks the bond between the different feedstock, and that results into production of hydrogen and some other gas species. And we also, basing on our previous result, we see some increase and then leveling off, but also we hypothesize that when you treat this feedstock for an extended period of time, then the hydrogen production rate will really increase up to a maximum, and then later on it will level off. So that was actually our hypothesis. So with that in mind, we really focus on the transact, on modifying the transact, because it operates on a lower flow rate, and also it's really easy to operate. So we actually devised what we call a streamer dielectric barrier discharge, and which is a modification of the transact, and this is actually the design. So we paid attention to the dielectric component because we wanted to see the effect of dielectric on the performance of this reactor. So this is the overall experimental setup. It's very, I know it's everywhere, but just quickly, so this is a system for the inlet flow rate of the gas in the reactor, And this is for the system for the outlet flow, for the gas flow and the gas products. And the gas product can be sampled here using the sampling bag, and this is to the exhaust. And this is the plasma power supply. This is the energy power supply to the reactor, as well as this is the electrical diagnostic setup. So some of the diagnostics we actually used was for the gas, we still use the gas chromatography, but also we wanted to understand more about the plasma. Then we use the optical emission spectroscopy, and solids also we used on optical, and then we use a field emission electron microscopy as well as a CNH analysis. And the condition was fixed 60 voltage level. The flow rate was 0.01 SMPM. We used argon, and the inter-electrode spacing was fixed 5 millimeters. And we treated it for 15 minutes for the 2 samples. Now, we wanted to know the effect of the dielectric on the performance of this reactor, and we developed an electrical model. So this is the actual imaging of the reactor under the operations treating the cellulose. But in this model, we assume that both the plasma, the feedstock, and the dielectric actually can be described capacitance, so that they can be described as parallel capacitance in series. And we develop an equivalent electrical circuit with this is an input voltage, this is an input current, and this is the plasma current. And this the capacitance of this dielectric and the feedstock can be geometrically determined, because we know the geometry, we know their geometry. But the problem was with the plasma capacitance, because the plasma is really very dynamic, and hence it was so difficult for us to determine to use a geometrical means, the geometrical approach to describe it. So what we did was, using the experimental data, we actually fed it to enable us to determine this plasma gap capacitance. So this is the equation which defines the plasma pore in terms of the plasma gap capacitance, and this is the total capacitance of the dielectric. Now the whole of this term is actually the total external displacement current, because you have this net capacitance, and then you have the alternating current flowing, and that results into the flow of current, which is we call it displacement current. And this is the displacement current within the gap. Now, so we had to take the different gas capacitance, and then we see that for a different gas capacitance, we see that the pore actually decreases a little bit, and then increases infinitely as the gas capacitance increases. Of course, this is as the result of interplay between the total displacement current as well as the total, the displacement current, the internal displacement current. And we assume that because the total pore, the plasma pore cannot be greater than the total pore. So with that, we were able to trim this interval, and with that we were able to define the interval, which is 0.1 to 2.9 picofarad. That's the gap capacitance, and using that we were able to estimate that the total pore ranges between 90 to 100%, which is very comparable with some of the literature. So we also look at electron, the spectroscopic diagnostics, which helps to determine the different plasma parameters, the electron number density, as well as the electron and excitation temperature. So what spectroscopy does is you see plasma because you have electron losing their energy, and as they lose their energy, then it is radiated. So the spectroscopy take that energy in terms of photons and count, and resolve them as a function of wavelength and the relative intensity. And this is just a quick snapshot. So we see relative intensity and then the wavelength. And these peaks are unique depending on which gas you're using. So for our experiment, we use argon, and this is typical of the argon. And we took those peaks. So in the determination of excitation temperature, we actually use Boltzmann plot, and this is the Boltzmann plot. Yeah, we have a lot of variables here, but this is the statistical weight, and this is the relative intensity, and this is the transition probability. So when you plot this graph here as a function of the energy of the upper energy state, then you feed it, the inverse of that line will actually gives you the excitation energy. Now, because this is a non-thermal plasma, so the excitation energy is not the same as the electron temperature. And we had to look around, and we adopted one method which has also been used by many authors, by Godillo, and where he used a modified, he actually modified the transition probability. So for every transition, you take all the possible transition and you sum them up. And when you plot this as a function of the upper energy level, the upper energy state, I mean, then you can, the slope gives you the electron temperature. And for the electron number density, we consider a model by Case et al., where they consider the electron number density as a function of input power, as well as the electron temperature. And for this condition, we found that it was, when you calculate this, you get 1.8 times 10 raised to 13. And we wanted to look at how does this electron temperature and excitation for the different treatment of this feedstock changes with the root mean power. And we see that the whole increases with the root mean power, but statistically they're more or less within the same range. And for the electron number density, yeah, there's no proper trend within this power limit to see that to see increase or decrease, but they are more all within the same range. So overall, we see that all these three plasma parameters are actually comparable, meaning that we had a comparable conditions. Now, we also look at the hydrogen production for cellulose and low density polyethylene using this as spark dielectric battery discharge. And we considered 4 different parameters. One of them is the cumulative production, hydrogen production. And this is the cumulative hydrogen production for cellulose, which increases more rapidly within the first 3 minutes and then trying to increase and increases steadily. And so for the hydrogen production rate, we see that the increase is more, it increases rapidly up to maximum of 40 and then reduces a little bit, start declining. And according to different authors, we see that the treatment of low density polyethylene actually occurs in 2 different, cellulose, I mean, occurs in 2 different regimes. So there's a devolatilization which results in the production of more volatile compounds. And then there's a Char reaction, which results into more charring. And we see that in the first regime, the devolatilization dominates over Char reaction. And according to Moon et al., he said that when you have the synergistic effect of devolatilization and Char reaction, that's when you have the maximum production. And the hydrogen production efficiency follows more or less the same trend with the hydrogen production rate. And the energy cost of hydrogen production, it's more or less has an inverse relationship as a hydrogen production efficiency. So at a higher hydrogen production efficiency, it has a lower energy cost, and in which case, this is 600 kilowatts hour per kilogram of hydrogen. So we look at also the treatment of low density polyethylene. Here we see that the cumulative hydrogen production increases with time, not more rapidly compared to the first phase. And the hydrogen production rate increases up to a maximum and then decreases. The overall trend is decreases slightly. And it's so difficult for us to have a distinct, the distinction between the 2 regimes. And the hydrogen production efficiency follows the same rate as the hydrogen production rate. And the minimum energy cost of the production is actually an inverse function. So this is 3 times, factor 3 times less than what we had in the first phase of our study. So we carried out a characterization of the solid samples. So this is the optical imaging. We use our camera. This is the cellulose. It's white and powdery, very sticky. But when you look at it under field emission microscope under low resolution, we see that this is actually consists of fibers, a network of crisscross crossing fibers with a lot of empty space. And this empty space actually depicts high porosity. And when we increase the magnification, we see that, these fibers actually consist of fibrils, which are really bundled together. And it is so difficult for us to distinguish them. So for the treated plasma, for the treated cellulose, it's really dark, probably during charring. And when you look at it under microscopy, under low resolution, we see that these consist of fragmented fibers. And under high magnification, we see that these fibers actually consist of protrusions. The fibrils are loosely attached together, and you can easily see them. They are very visible. And when we measure the diameter of those fibrils, they're about 50 nanometer. And then for the low density polyethylene, it's smooth, as you could see, but on the field emission microscopy under low resolution, the surface is more smooth. It's dense, not porous, but also we see some kind of peeling, and that is attributed to mechanical damage during the sample preparation, because I used the pellet to remove it. And under my high magnification, we still see that it's dense and actually less porous. So for the treated low density polyethylene, it's consists of a kind of embedded migraines, and that was really also very interesting to us. And when we zoom it more, we see that these are actually migraines which consist of their dimples-like structure, and this is it's interesting. And with that, here are my summary and conclusions. One, we designed two non-thermal plasma reactors with complementary characteristics to produce hydrogen from low density polyethylene. And we also saw that the voltage level significantly affects the performance of the reactor. But overall, the performance of the two reactors were comparable. Now, basing on our previous studies, we devised a streamer dielectric barrier discharge, and the electrical model indicates that 90 to 100% of the power actually goes into plasma. And for the treatment of cellulose, we see that there are formation of two regimes: devolatilization and Char reaction. And lastly, we also saw that the energy cost of production of cellulose was half that of low density polyethylene, basing on its thermophysical and chemical composition, because the low density polyethylene is thermally very stable. And this is the recommendation for the future work. Incorporation of catalysts would help to may help to improve on the performance of the process, so that has to be investigated. And also looking at the different morphology of the feedstock, whether film powder, also I think it's important. And other spectroscopic analysis, such as continuum line spectrum and line broadening, can also be used on one, besides the Godillo approach, and the geometrical effects of the feedstock and the dielectric has to be thoroughly investigated, and comprehensive characterization of the plasma treated solids, especially those migraines and the fibrils. I think they can further be investigated. They seems to present some promising elements. So these are some of the presentations as well as published papers. And with this, I would like to say thank you, Professor Juan Pablo Trelas, for all your support during all this time. You did it all for me. Thank you so much. And my committee members, you have been there for me. Thank you so much. My friends, Re-Engineered Energy Labs, and all my friends within the UMass Lowell, thank you so much. The room is so big. I'm so happy. And then my friends outside UMass Lowell, thank you so much for putting all this food together. And my family in Uganda, thank you so much. And to my sponsor of the project, US Army Capability Combat Development Command, thank you. Fulbright for sponsoring my studies, thank you. And everyone, whether on Zoom, any part of the world, thank you so much.
Thank you very much, Benard. So the floor is open for questions from the general audience. Question general, any clarification?
Not yet, but thank you.
Let me start with Benard. I mean, when you show for the design and characterization of these two reactors, right? You play with these thermoflow analysis, right?
Yes.
And they was, some quite a bit of heating. How relevant is that? You're saying the reactor is at relatively low temperature, so they not for cooling or heating, right? This in temperature would be beneficial. What are your thoughts about from your analysis and that moment?
Good question. I think increasing the temperature to a bigger degree would really result into extra cooling, and that would actually increase the cost of the reactor, the whole process. And also, secondly, when you look at what we're using glass quartz. I know maybe for the industrial application, maybe something else, but in that case, so when the temperature increases, you're putting a lot of thermal stress on the reactor. So that may that won't be really good in the process. Yeah. Yes. Thank you. Thank you. Thank you so much, Majid. Yeah, that's actually a very, very good question. Yeah. We produce different gas species alongside hydrogen. And with our current focus, we were basically focusing how we can really produce it, but not moving at the point of separation and eventually using it. So that I think that's the next phase of the research which we do not look at. Perhaps Professor Wong, maybe that's his area of expertise there, but that was not within our scope of the studies. Yeah, but that's really good because I know you are using lean hydrogen, like you're using lean hydrogen. Yeah. Yes. Yes.